Okay, it says that we get data. Just see here. Okay. We will start the stream really soon. Wait, just hello. Wait, can you? So I need to copy the link and share it. How do we do this? Where do we need to go to YouTube? Yeah, the stream will start in like 5 minutes. We will see on the Creation Olympiad just finished. I did not have time to I actually forgot about it, so I made some other arrangements, and unfortunately it's I didn't compete. So the last year I solved this last problem, the persistency problem, was a really nice problem, and this year I think they're probably they had really nice problems as well. So yeah, and just post it here. Also I want to post something. So what's that? Why doesn't YouTube, like, do I need to go here live to show the... You didn't compete as well, yeah. Yeah, what we can do, it's yeah, now I see the chat. Let me just arrange my windows better. Okay. It's actually a hard Olympiad. It's 3 hours, and you need to be mentally prepared for it as well. So it's not that easy. I actually loved every round from Tsotsi. The problems were really good. Okay, so I just share it. We will today try to solve one problem. I haven't solved this problem, so yeah, basically, me too. It's the faculty and the job as well, so rarely get the time to solve. But Cold Forces, it's just good to always continuously solve. Let me just find what is this. Oh, I'm not good at ordinary technology, so you can excuse me a little bit. Okay, so I mean, we could take a look just at if they have from Tsotsi, if they have some rating lists. So let's see. Instead of round 2, I could go and see the Olympiad. Oh, where is this? So past events. Where can I see the Olympiad though? Oh, active for future events. What? Wait. How do I see Creation Olympiad Informatics 2023 scoreboard. How do I see the scoreboard? But if you're not in the Olympiad, you cannot even see the scoreboard. Is that correct? Well, I don't know. Like you could see the results here from other rounds. So I would think that you could be able to see it even if you didn't compete. As far as I know, you. Is that the case? I mean, that's bad if I can't see it. And wait, you have the tasks, but you don't have any test data from the last Olympiad. That's weird. Hello, welcome. We will today talk about an easy way to understand. We were looking at the Creation Olympiad just finished, but we will talk about an easy way to understand centroid decomposition. It's and we will try to solve this problem, even though this problem is like rated 2400 or something like that, so it's not really an easy problem. I would show you, maybe we wouldn't be able to solve it today because I don't know how much time we have, but I will try to solve it. But I will show you like how I think about when I approach problems in this with centroid decomposition. And I learned actually this in the competition not long time ago. I learned how to like actually imagine this a much better way, and like what you have to do in this kind of problem. So this was like we had on CERTS, we had 2022, we had a problem where you, if I will pull it up, so you know, like I will explain first what kind of problems centroid decomposition usually apply to, and then we will try to solve. We will actually like go through the steps of somehow reimagining the way centroid decomposition actually works. But CERTS 2022 had really interesting problems, and one of them, this here. Let me just find. Where is this where the judge system is? So 2022, this problem, the bandits. Let me see if you see the. I think it's fine. You see, it's the text. You can see the text, right? Yeah. So let me just okay. Okay. So the problem is essentially you have some weighted tree connecting from connecting the ith road connects some vertices A and B with some length C. Then you, although this problem is like really hard, but just to grasp the concept of centroid decomposition and where it is used, we will show you this problem. We will not try to solve it. This is a really hard problem. But just so you know where centroid decomposition is used. So you have some queries essentially, and each query is essentially of two types. There is one query that says on vertex xj in radius rj, so some radius, so in some radius around this vertex, you want to add +1, like some like +1, so range addition on this radius. And then you want to, the next query is this question mark, which is followed by yj, is the number, is like in this road, so in like this edge, how many +1s do we have? But because the tree is weighted, the radius doesn't necessarily end in a node. It could end in like a half an edge, and this edge will still count, I think. This thing of having something that is connected to the distance from some node is very usually the theme in centroid decomposition problems. So we have something that we have some query on some distances from some nodes. In our case, if I open up one node, in our case, in this problem, I think as far as I remember, it was like, okay, you have this node, and then you have some other nodes here, and in some radius. So in some radius, let's say it's like this, you add +1. But this, if this length is very, very large, it might be up to here. Then here, let's say this is like 100, then like this is 400, then it could be like somewhere here and then somewhere here. So in some radius up about this node, you add +1 here, and then for some edge here, you want to query how many queries does this edge actually is inside. So you can see the idea. You can see how this distance from one node is connected. But this problem is very, very difficult, and I won't recommend solving it for beginners. But I will show you. I will first show you how I imagine centroid decomposition. Then we will show you what's the biggest problems in centroid decomposition, and then we will try to solve this problem. So centroid decomposition it can be boiled down to one thing. Even if we don't know centroid decomposition, let's assume that we have no idea what centroid decomposition is. So many of you may be watching this video have no idea what centroid decomposition is. But many times you will be asked. Let's say we will simplify this. We will simplify it as much as we can. Let's say we have a node, and we are asked about how many paths through this node pass. So if I have a tree, let me just draw it like maybe here, let's see, here, say here, let's add one more here, whatever. And then, okay, I'm asked about this node. And if you're asked about, let's say the problem asks about one node, only one node, so you don't have queries, you don't have anything, only one node. And you say, okay, how many paths through this node pass such that let's say each vertex has either a white color or a black color. So let's say this is a white vertex, 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 and all of the others are black. And then we'll say, okay, how many paths through this node pass such that both vertices on this path are white vertices. I mean both endpoints on this path. So a path could start here, could go through these nodes, then could end here. And this is a valid path that passes through you. So how would you solve this problem? If you have only one node to worry about, and you only care about the paths that pass through this node, and that one endpoint is a white node and the other endpoint is white, they can pass through a black node. So you could have like this again. This is another path. This is another path. So all of the paths, you have to enumerate them somehow, but through one node, only through one node. So only through one node. So we could essentially even use this some of an approach to not enumerate all of the paths. If we take a look at how many of the paths, what is the maximum number of paths they can be, it can be n squared still in this approach, because you could have every node could be a white node, and you could have this node have here some n half nodes which are white, and here would have n half nodes which are white. Then this is n squared. But what else can you do to simplify this, to count them for this node? So could you just in the comments maybe just give me some ideas? What you may know already what is the solution to this problem, and we're talking about only one query. We're not talking about Q queries. We want to just first start from the beginning. It is a tree, right? Centroid decomposition is done on trees. It's done only on trees. There's no, I don't recall such things on graphs. There are global minimum cuts on graphs, but that is not a centroid decomposition thing. But it is a tree, yeah? So we have to enumerate all of the nodes that pass through this. And this is a nice example to start thinking about how we could do this for n nodes. And not only this, you would then apply some other data structures such as maps, tries, whatever, segment trees, some other data structures to even make this even a more aggressive strategy. But how would you enumerate this so how would you count these nodes? So you have like, okay, the n goes up to 10 to the 2 times 10 to the 5. You have one node which is let's say u, which is like, or x, some special node which goes up to n. Then you have some, for each node you have either it's a white or a black node, so you have 1 or 0, like you have some string. And then you need to find these paths that go through the u node, So yeah, so how would you do this? One way that I can think of is to start from the leaf nodes and with the highest depth, keep going up and sum up the white nodes that we have. And when we reach U, that is the root, we just multiply the pairs. Yeah. So yeah, this is hey, what's up? So yeah, this is the approach. Blogger says this approach. You do this. I will explain this approach. What he said right now. But first of all, we could just realize that it's way better to root the tree at the U node. It's way better to root this tree here. Why? Because if we root this tree here, what we can do is, we know that we don't care about the parents. We won't have any parents to worry about. So if I root the tree in some unode, is it similar to segment tree or family tree, where everything you can do with family tree is also possible with segment tree, similar to heavy light and centroid decomposition? No, actually, if you know heavy light decomposition, you not necessarily can solve problems which are solvable with centroid decomposition. So it's or vice versa. There are problems which centroid decomposition is usually. I will mention this. The centroid decomposition is usually harder to compute. Not necessarily that you may not be able to solve heavy light decomposition problems with centroid decomposition, but it's more of like it is very hard to compute. We actually don't have to go to the leaves, just on DFS. Yeah, that I will just now say. But first, I will want to mention that heavy light decomposition is different because heavy light decomposition works on paths. Many times we apply this on paths, and then we want to query something on other paths, and we say, okay, there will be log n paths, such that we need to query, and then in each query we have log n time, so we have log square n time in heavy light decomposition. Here we also have this, but here this approach on centroid decomposition is much different, much more different. There are no this paths things that go, but we are now somehow dividing this tree and doing much more on radial things. We work on radial things, and even though we have some paths, but we will explain everything later. First, there are two approaches, and they are completely different. They may solve some usually some problems. Maybe it's the same problem, you could solve it with two approaches, but you rarely see this. It's either heavy light decomposition or centroid decomposition. Okay, so what Blago said, if I have a unode and I root the tree, because I have only one query, I could root this tree in this unode, and this won't change the composition of the tree. We know that a tree can be rooted in any nodes without changing its composition. It's still the same tree. So I could root this tree in the unode, and what I could say is that, okay, I have some white nodes here. Let's say these were white nodes. What it's always practical to imagine is not to imagine the whole tree, but to make this representation of the tree much better, is to imagine it like this. You have a unode, which is the root, and then you have some subtrees here. And you always want to imagine these subtrees as like triangles. So this subtree here, what we are computing in this subtree, it's very different from what we are computing in this subtree. They're not connected in any way because there are no cycles. So what we can do is count the white nodes in each subtree. So let's say we have here three white nodes. Then, okay, we had what we had here. Let me just see. So we had here three white nodes. Here we have two white nodes, and here we have one white node. And the paths that go through U can be easily counted with some mathematics. And what I always do is I always sum up all of these, and then I call one, like, okay, how do we count first the white nodes? We go DFS. We start from the root node, and we go into this subtree, and we count all of the white nodes. Then we go into, let me just draw this like that. Then we go into this subtree, and then we count the white nodes here, and then we go into this subtree, and we count the white nodes. And now we need to connect some white node from this subtree to some other white node from this subtree. And how you count this is by you can sum up all of these, and then when I'm actually counting the white nodes from this tree, or you don't even need to sum up all of these. But let me just explain why I do this sometimes, because that will be useful in the centroid decomposition that comes later. So what you can do is sum up all of these, 6. And then you could start from this subtree, and then from here, there are 3 nodes. That's 3 paths that start from some 3 nodes here in this subtree. And then what I do is I do 6 minus 3 is these all other subtrees here. All other subtrees except this one. So this is like except myself. So how many nodes are except me? And this is like 3 nodes in this case. So there are 3 nodes except myself in my subtree. And then 3 nodes are, we know that 3 nodes are in my subtree. So it's 3 times 3 here. This is one computation that I need to do, that note that there are paths that start in my subtree and end somewhere else and go through you. So we are counting paths that go through you. Okay, so this is one computation. Plus, there are 2 nodes here, and except myself, so there are 2 nodes that 2 paths, 2 start points here, and there are 6 minus 2 points which are outside my subtree. And I do this for every subtree. You could do this in the time of the subtree. Yes, no. There is one other technique. So here, when you do with the sum, so when you sum up all of these, you have to be careful that you're overcounting actually, because what you're doing here is you're saying, okay, 3 nodes start here. There are 3 endpoints that start here and end somewhere else. But when you come to a 1 here at the end, you overcount the paths that end in 3. And then when you do all of this, you have to divide it by 2 because you overcount. Yes, you can't like do n squared on this, but what another technique what you can do is that you can prefix it. So you do like 3 times 0, then you come to here and you say how many on the left side. Okay, we have 3 on the left side, we come to here 2 times 3, and then we come to here, then there are 5 on the left side, there's 1 times 5. And this will be the same result as what we are computing here with the division. This will be the same with the same result. It might be much clearer in some instances, but we will see in other times, in other data structures, it's actually much more efficient to make an exception of one subtree from a whole data structure than to have these prefix things. But either way, it's possible. So either way you compute this, it won't matter as long as you're not iterating, as Blagoy said, n squared times through all of these subtrees. So this is approach how you count the paths through a root node from one subtree to any other subtrees. This is the same approach we're going to use over and over and over and over and over in centroid decomposition. Okay, but this is no centroid decomposition. Now we have only one node, and this is one thing which we're doing, right? We're just counting, and it's all too slow. Okay, so why centroid decomposition even works? I won't go into the proofs of why centroid decomposition even works, but essentially what is the main takeaway of centroid decomposition? The main takeaway is if I have some tree, which I won't denote as a tree, I won't just write the nodes, but I could have some tree. So this is like a big tree here, like blah, 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 blah. It doesn't matter, right? As in any hierarchy, in any company, in anything, if you could divide the work through different to different people, it would be easier to compute, it will be more productive in a way, right? So let's imagine, imagine if we could just slice the tree in half, and we could somehow make some node here a president node. So like I would make one president node, which would be a president to the whole tree. So this node is a president to the whole tree. This is like the king node, the kings of the kings of the kings. So this is like the kings to the nth power. This is like the most powerful node, right? And I slice down the tree to this node, and I say, okay, for simplest sake, I will say that I slice down in two. But okay, we'll see some other complications, but it doesn't matter. We'll slice it at least in two. So okay, so we have the king node. So this will be like this will be the king node here. Let me just be really. No, I want to draw it well. That's not well drawn, but whatever. Let's say this. Well, this is king to the nth power. Okay, and then we will say, okay, we will divide this. And here I will make some other node, which is another king, but this king is not that powerful. This only cares about the half of the territory of the tree. This is only n to the half power. And there is another king here that cares only about wait, what the fuck? That cares only about n half. And you could see how this could be actually like even more. I could divide this territory in half, so I could have this in half here, and this in half, and then I could make some other kings here that are king to some territory. Essentially, I don't know anything about the tree. I just know that there are at most log n kings. If I'm some like really poor, person, some slave here or whatever, I don't care. Now I'm gonna be cancelled here, but whatever. Like I'm some really poor person here. This is some soldier. I at most would contact log n kings until I come to the president of the tree of the country. At most log n. Why? Because we are dividing it by half. So we have this king is at all of these all of n nodes. Then this king is n half. So this king is only responsible for half of these nodes, and this king is only responsible for half of these nodes. And then this is like n fourth. 1/4 of this, and then you come to this soldier, and even the soldier is a centroid. So all of these kings are actually centroids. All of these. Okay. So how do you okay, so how do you compute this? And like, okay, we saw that log n nodes we need to contact until I get to the president. And essentially what I'm saying that if I want to change something, I need to log n times to provision this change up the chain of command, what we're saying. It's for educational purposes only. Yes, it's for educational purposes only. I mean, even if I get cancelled, it's more of I will get more fame probably if I say some stupid things like that. So, but yeah, so it's this chain of commenting. But this is not the representation I want to show you guys. This is one representation that no one shows. No one shows you how this is in like the way it's like. It has to be this. When I learned this from the codes from the Polish guys, one Polish team actually like had this centroid decomposition for this problem written for this A bandits. And when I learned this representation of centroid decomposition, I was like, wow, like I finally get it. But this is not the representation how I learned centroid decomposition, how I actually got what centroid decomposition is. I got it by another representation. I will show you. It's a really cool representation. And when you learn this, you would never like, you will always know what to do in centroid decomposition problems. It will be like, aha, okay, I just have to do this. It's straightforward. That's it. Okay, so how you want to imagine this? Okay. It's very interesting representation. Imagine that we have some kink here, some centroid here, which is some kink. So this is some kink. We don't know to what power it is. Like let's say to some power, and I don't know. It's like it doesn't matter. It's some kink. This kink is responsible for some villages, for some like, it's not villages, but like some subtrees. But I call them villages. Like some subtrees is responsible. Okay. Let me denote this kink here with like some. Also, I will need. Okay, let's see. Whatever. Let's see, like this. This kink is responsible for some villages, for some subtrees. Okay. In these subtrees, I need to be very fast in computing my answer, and my answer would be like always would be in some like, if I want to, what we were doing in the first example, we were counting paths that go through this root node. Always you would do in centroid decomposition, you will do something like this. Either counting paths that go through a root node, or counting paths that go to a root node, or counting paths that like do something through a root, through this centroid node. So essentially it's like, okay, if I have a node here and there is a path that goes through this root node, it could end up in any of the other subtrees. So take in mind that this is not the whole tree. This is just a part of the tree for this leader to be responsible for. So this centroid is responsible for this part of the tree. And we have some path that starts in some village, this leader is responsible, and ends in some other subtree. But this is not the whole tree. So we could have a query that starts in one village and ends up somewhere else in the tree. And keep in mind, we're not talking about the centroid tree here. Centroid tree is only an abstraction of what centroid decomposition actually does. But we're not talking about, this is our tree. We're not talking about the centroid tree. We're talking about only our tree. What actually this says is that there is a very important edge. I call it a backdoor. And this backdoor actually connects. This backdoor, let me just do this, connects some other subtree, some other village that is up to the how do I do this? This backdoor. So I got here, I got like, let's say here, I got here, then I got some here, and then I connect this backdoor, and this backdoor connects to a centroid which is the leader of this guy. So this is double leader of this guy here. Why? Because when we did this guy here, when we somehow gave him the order to recursively cut down the tree, what we did is we went, this subtree here is a part of my leader, it's one of his subtrees, right? So it doesn't necessarily, the leader isn't necessarily connected to this guy immediately. It could be, but it's often in some subtree, it's connected to some subtree that this guy is responsible for. And this leader is also on the other side, is also connected to some other subtrees the same way. But we don't really care about these subtrees. It's like, if we take a look, it's like there is another centroid here. There is another centroid here. And all of these centroids have a backdoor to this leader. Okay? All of these centroids have some backdoor, but we don't care. If we can calculate some information about these whole subtrees, except my subtree, my village that I'm responsible for, this guy is responsible for, except mine, the same way we calculated for the first task, the same way with the subtraction or whatever else we could do, the same way we calculate for the first task, we will calculate this. We will know that because this leader will be computed first, we will calculate to some subtrees here, some information through these subtrees, and then this subtree here that we are responsible for will already know how many paths come through here. And then all of these paths, because are computed through the leader node, we already know them, how many are there, and then we can account them as if they were in this subtree, as if they were here. We can account them, and we can connect them to our subtree. So essentially, what we are doing is a hierarchical approach upon a tree. So essentially, we're dividing the tree into some hierarchies where some guy is responsible for some villages or for some other trees, and then we're somehow connecting. there are two things to remember. There is this thing that paths come from a village, from my village, from one of my subtrees. So there are two things. The first thing is there are paths that come from one of my subtrees to another. And there is a second thing from one of my villages to the parent centroid. This from one of my villages to the parent of centroid. What you cannot do, you cannot count, is paths that are coming from here to the centroid. So I cannot count this path. Why is this path? Why I cannot count it? Because it doesn't pass through me. It has to pass through me. I have to count. I have to only be responsible for paths that pass through me. It's always in these problems like this. If I need to count paths, it's only because this path that comes from here and it comes like that will be counted in a centroid inside of this subtree. So it won't be counted in a centroid, it won't be counted in this centroid, but it will be counted in the centroid inside this subtree. So yeah, so this is like how I like how to represent like centroid decomposition a better way. I mean, it's maybe much more like complicated now on a drawing, but you would get the approach if you just solve one or two tasks with centroid decomposition. It's pretty common technique to go through these like log-n centroids, and like this is the way you go through them. You go through them because there is some centroid here that is responsible for some village, then this path goes through him, then it goes through him, then it goes through him, until it goes maybe to some other centroid to the parent. But because we have all of these pre-computed for the parent centroids, we could easily find out what is for the children centroids. It's essentially decomposing this path on log n other smaller paths. But what you could have in some problems like this is you could have data structures for each of these subtrees. Or maybe not data structures for each of these subtrees, but yeah, a data structure for each of these subtrees. You could have some maps here, or you could have some segment trees. Why is this efficient though? Okay, so we have like we have log n centroids. Each centroid, log n levels of centroid. So level is like this guy and this guy have the same level. These three guys have the same level because they're all centroids that come from this guy here. And because this level, this guy and this guy and this guy have the same level, we could have only log n levels, and each log n level we have times n nodes, in like n computation steps in this. So log n levels times n computation steps, but you could have sometimes here like log n if I need to compute something like maps or something like this, maybe log square n. That's why the centroid decomposition is very hard to compute. If you notice, centroid decomposition problems usually have 3 or 4 time seconds limit, because they're because of this, because of the multiple logarithmic factors that add upon the centroid factor, the centroid logarithmic factor. That's why centroid decomposition is hard. Also, yeah, also, that's why it's like you could understand now why there are not many problems with centroid decomposition. If there are a lot of so if you think of problem that could be solved with centroid decomposition, there could be another technique that solves this problem, and maybe even faster. So that's why it's hard to come up with problems that are only solvable with centroid decomposition. You could see the time limit 4 seconds here, and sometimes you would have like 1 gigabyte. So like one A bandits have like a half a gigabyte of memory in 5 seconds to solve. Even though like you use in this problem, you use like segment trees, you use like trees, some data structures that which are like order sets. They used order sets here, but you could solve this with trips or some other fanfic segment tree, something like that. But this is really computationally heavy task, and you have to be fast when computing these things. It's my recommendation is when you see a problem like on IOI or some other like subtask Olympiad, my recommendation is first like try to maybe solve the problem for some task which like doesn't have queries or has one query, or like maybe like this, just to come up with the idea of like how to do this, and then you could extend this idea on centroid decomposition. If you knew how to solve this task here, what we're talking about this with like a deficit approach and just counting numbers, and then like computing this like the sum except something, so except some subtree. If you like are comfortable with computing these things, then you could go this, and instead of this u here, you will have like just log n centroids, and that's it. You would compute for log n centroid something. You have to be careful here in this case where you would need to access this backdoor. Some problems don't require to access this backdoor. In such counting problems, if you have counting problems, many times they don't require access to the backdoor. Other problems which have like assigning queries, they do require to be changed not only on this tree, but also on like log n steps upstairs to be like computed and accounted for, and have this like access to what I call the backdoor. Okay, and you have to be careful about this. So you have to be careful. So what if you have any questions? Maybe here is a nice time to recap everything. Then, because it's already like an hour, then we will go to the problem. We'll try to solve it, but yeah. So we know this. There are one path that comes from one subtree to another, and there are one path that comes from one subtree to through the backdoor to my parent. There's some paths that I need to account for. Okay. That's what can happen. All this here is not really usually accounted for. Like this usually accounts, the parent usually accounts for this, because the parent is also accounting for this node. Here, don't forget that the parent, this node is also a soldier for the parent. If you can understand this, like the parent has like, imagine like this subtree is like a copy of this subtree. Like what I'm doing for these subtrees here, what I'm questioning is also like in the parent node. And if I account all of the paths that go through this subtree and to other subtree, then I don't need, actually this path is accounted in the parent node, right? It's just that simple. So I need to account all of the paths that go from one subtree to another subtree in my centroid. Okay, so yeah, so but you need to imagine the centroid tree as not a, so this is not my centroid tree. This is my tree. This is not a centroid tree. A centroid tree is just like if I take this parent and then I add a connection to here, and then if I add connection to here and I add connection to here, and then this will be my centroid tree. But not necessarily the centroids are connected to each other by edges in the real tree. Okay, so this is how I understand centroid decomposition. This edge, this backdoor doesn't really exist. Like when you're doing centroid decomposition, you can remove edges or you can block nodes in order not to visit them. Again, I usually block nodes. But this like edge doesn't like this technically exists, but it after the centroid decomposition processing, this edge doesn't exist. So you could basically I mean, yeah, you need to go through the edges, but basically what you will have is some data structures that represent these subtrees much sparser. It's not like the whole subtree, but some data structures represent. So what I will actually do is I will open up this problem. So read it, you guys read it. I'll explain it. I need just to go to the toilet. So you guys read this problem, and then we will come back and discuss my ideas for this problem, and I will try to solve it, and then you will see how this centroid decomposition works in real life. So yeah, I will just leave this problem here. Oh yeah, I can link the problem. Yeah, I can link the problem. Whoops. Wait. Yeah, of course I can link the problem. So yeah, you try to think about this problem, and then we'll try to solve it. I haven't actually solved it, so maybe we will, maybe we won't. So yeah. Okay. Okay, excuse me just for a moment. I hope you had enough time to think about the problem. Do you have any ideas, first of all, about the problem? So what will be the first? So the problem is you're given a tree. So it's a connected acyclic undirected graph and vertices. Then each vertex is assigned some character from A to T. So that there's immediately some suspicious here, right, from A to T. A path in the tree is said to be palindromic if at least one permutation of the labels in the path is palindrome. For each vertex, output the number of palindromic paths passing through it. So for each vertex, you have to calculate some paths passing through it, and immediately the first thing you need to come to mind is like centroid decomposition. Although, like, I mean, if you would only compute some paths passing through one vertex, I said just root the tree there, and you're good to go with one DFS. But now the paths passing through each vertex, it's not that easy to compute. Okay, and the sample cases are like this. So a given tree, and then for each vertex you have like from A to T some character. So first of all, from A to T, we could just you could just do this, and then you would see that there are 6 more letters up the alphabet, so technically you have 20 letters from A to T. Yeah, so 20 letters. So okay, so what are the first observations? We're gonna just go really quickly. I don't know how much time I will have to solve this problem, but I may just end the stream really closely, like to 1.5 hours, because like something came up, but I could tomorrow I could or something like do another stream, but I would want to solve this problem quickly. So I mean, it's not an easy problem. First of all, some of my observations that I came up with when I read this problem, I read it today, so didn't have really time to think about observations. But first thing is like, okay, 20 letters, so we know like, okay, 20 letters, that's not a lot, but it's not small. Okay, I still don't know why 26, because in my solution like 26 should work as well, but whatever. Another thing is you have to consider what is a, if I have some path with some letters on it, when is this path palindromic? So if I have some like path like this, so when the first observation, okay, when is this path palindromic, right? Can we define when is this path palindromic? So we can define this path being palindromic if at most one vertex appears odd times. If at most one letter appears odd times. Yes. Okay, yeah. So we can define this path as palindromic. Yeah, exactly. If I see the frequency arrays, yeah, the frequency arrays, I have some frequency array from A, B, C, D, E, F, G, blah, 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 blah. Okay, so how many A's are there? There are 4 A's, right? There are 2 B's, there are 2 C's, there's 1 D, there's 0, 0, 0, blah, blah, blah. Okay, so we can immediately see that we are just interested in the parity of a path of this array, of this frequency array. If I have 2 A's, we could arrange them at the end of the palindrome. If I have two B's, we could arrange them and boundary. Because we can do any permutation we want, it doesn't really matter how we do it. But if we are interested only in the parity, we could say that it doesn't matter if I have 0 A's or 2 A's or 4 A's. It doesn't matter. So we could convert this into a binary representation. When I have an odd number or even number of A's, we will have 0, and an odd number of A's will have 1. Odd number of things of an odd number of this letter. So the trick here, okay, if I have if I have this binary string, there could be at most, as you said, at most one. At most one. Yeah, exactly. Okay, let me just, okay. Most one. Okay. So if I have some paths, if now I represent this as some U node, which is a centroid node, and I do in our representation, we have some subtree here, we have some subtree here, we have some subtree here. From this to count the paths that go through U node, I can start in any path here, go through the U node and end in any path here, or go through this and end in my parent node, in my parent centroid, in some other subtree that the parent centroid is responsible for. Or go from here to, let's say, here, whatever, doesn't matter. So essentially what we need to do is to somehow count. If I just take a look here in these subtrees, I need to somehow quickly count how many such paths exist. One thing you could immediately see is that if I have some new node, one thing we could immediately see is that we could somehow, how do you say this, simplify the problem into like, okay, if I have some paths here that come through this to this U node, if I have some path here, and I have some frequency array for this path, let's say like this. So this is some frequency array. This is for the red path. So this is like for this node, I have some frequency array. Then I need to match some other frequency arrays in some other subtrees, some other paths. I need to match them that have either the same frequency array. Here it's either the same frequency array or one thing is changed, such that like you get like, if it's the same frequency array, then A, we know that A XOR A is 0. But if one bit is changed, it's like this guy has the same guy, this here is A, but it's XORed in one place, in some place B, or no, maybe I, whatever. In some place I, this A is XORed, and this here is the same as A. And then when we do A XOR 1 I, we get this is 0, and then this is 1i. And then, okay, this is a palindrome. This path can be a palindrome here. Okay. Also, this is done. This is also true if we have the backdoor to my parent. To my parent centroid is here. This is my father king. this is in some tree. This is also true because my father king would have some data structure which stores these possible representations, and now I have to match these possible representations with any of my other possible paths here, which are not in this tree, because I cannot go from here to here, because this path doesn't pass through you. It has to pass through you. It has to pass through me, through this tree here, through my thing. And now the problem, there is another subtask here, right? You're given two dictionaries. You are given two dictionaries, and then you have one dictionary. You have all of these, and then the other dictionary. You have all of these, right? The problem is now how many matches can we go through these dictionaries, through one of the dictionary and the other dictionary, in order to get either the same thing in both dictionaries or one thing different, one bit different. So how do you quickly enough do this? How do you quickly enough do this? Now, here you could just say your ideas in the comments section below. So whenever you want, it doesn't matter. The one thing is that you could do this. I will maybe in some other videos I will show you data structures that does this in very fast time. But essentially it's not worth here computing this in fast time. It's enough to have one of the dictionaries, and usually usually how to optimize this is you would get the larger dictionary. So let's say that here we are accessing this backdoor, and we have two dictionaries essentially. One dictionary is this guy here, so it's like everything except this guy, except my subtree that the backdoor is in. Then another dictionary is on the parent except this child. And this is another dictionary. This dictionary is usually way bigger than my thing here, my small children here. And to compute this, what you could do is go through the smaller dictionary, and you could search in the big dictionary in log-n time. Here it's not really a log-n time because you need to search for, like, what if a letter is changed. So for each letter here, you would flip it and search if there is a string such that this here is inside of this dictionary. And then you would go and flip the other letter, and then you will see if it's inside of this dictionary. So this is like somehow what I was thinking on my approach. So the complexity here is quite big. It's like log times 20 or something like that, and log times n log n times 20, which is one more log n. But it's, I would say, quite fast, considering that yeah, VS Code setup. There are a lot of people that ask me about like the VS Code setup. It's not that difficult to set it up like this. I could make a video on the VS Code setup. So quickly, just have the CPH judge, competitive companion and like a Sigwin terminal and some few other configs and things in the background. But it's yeah, maybe yeah, sure. Yeah, so the thing is like, okay, so how do you say that this would be enough? Because we are searching in this huge database here in this one of these dictionaries will be huge. The other dictionary is small. It's only like the subtree that we are actually answering to. And because we are doing this in like every node, it's like the nodes actually have very small subtrees that are responsible for. Only like very few nodes have like, because of the log n factor, it still is represented here. It's still n log n. So maybe let's try to call it. See where we can go. Now I have this one snippet that I use for Centroid Decomposition. I don't know if that's actually somewhere. I think from some blog or something. I think you could find it here somewhere. I think it's this. Is this? Yeah, I think it's this. I just made it into a better snippet, so I can just like reuse it. I just copied the code and a little bit like changed changed this, and I changed. I'm not erasing edges, which is like slower operation. I'm flagging them. I'm flagging nodes as I have been visited, and this operation is quite quicker, in my opinion. Although this erasing of edges is maybe better, because then in the Centroid node I don't visit this edge, but this edge will be visited almost log n time, which means I think it's the same. I think either you erase or you flag the node as erase. I think it's the same. Correct me if I'm mistaken somehow. Correct me there. I'm not sure, but I think it's the same, because log n time you visit some Centroid which can be connected to this edge, and then you kind of want to. But maybe this. But maybe this is even faster. And not the deletion of edges is also n log n, as we only have n edges to remove in each edge removal. Now this I'm not sure. Like this I'm not sure. Okay, it's like, yeah, this is n log n. Yes, but if I have like. Although like I have solved a couple of problems with like this approach where I flag the edge as checked, and you need to check this to check this flag everywhere. I'm not even sure if this is faster. This might be actually okay. This might be actually like okay if you just like have this set. So I recommend this maybe approach to Centroid Decomposition. You don't think it matters? Yeah. I mean, yeah. Yeah, I don't think it matters either. But it would. I would take some time to prove it, maybe. That it doesn't matter. Okay, so. Okay, so let's see how we should do this. Maybe we should grab something easier. Yeah, I have something here. Where was this problem. 3. So let's just delete everything that here is not necessary, so we can start from the scratch. I don't want to rewrite everything in the Centroid decomposition, but maybe like just this. And like we don't have now modifiers and queries, but we will have like a query thing. We won't have like query. We could do this as soon as the Centroid decomposition is done. I mean, not as soon as it's done. It's like we could process this in the same run as the Centroid decomposition. That's what I want to say. Okay, so distances, we don't really matter distances. Let me just delete everything. Answer here, answer. Let's say that answer is okay, let's say infinity, whatever, doesn't matter. What we need the G is our tree, size is our size of the subtree, parent, answer, and is it visited? Is it in upper level? This is one of the DFSs. The other DFS, the build procedure is here. The centered procedure is here. Okay, add an edge. Okay, so I need to build it here. Don't forget this. Don't forget calling the build step. Always forget calling the build step. Okay, so what's the idea here? Let's go through the code in order just to get our hands clear to the code and to our representation. We have this build step. This build step is like the first DFS from the Centroid decomposition. Okay. So the first thing to do is when I have a tree here, when I have some tree, I first need to know the size of the tree that I'm working for, like the territory of the tree that I'm responsible for. And this is the first DFS here, what it does. Like this DFS, it only computes sizes. Okay. So this is some size. And this says, okay, there are n nodes that I'm responsible for. Now I need to compute the centroid of these n nodes. So the centroid is computed in this procedure. It's again, we're going to DFS, but we're actually checking when this size is equal to n half. When this size is like equal to n half, we can cut that. We can assign this as our centroid. We can essentially cut it there, right? So we get some centroid, right? So we cut it. We get some centroid. Then what we say is, okay, the parent here, whatever, it doesn't matter. We want to process everything in the second DFS. So the second DFS is, okay, this centroid, we got it. This is the king of the kings of the kings, what the king on the nth power, when we said, whatever, doesn't matter mathematically. But this guy has some subtrees here, and it could have a lot of subtrees. I mean, it isn't guaranteed that it has 2 subtrees. It could have more. And we essentially want to do DFS now as from his point of view. So his point of view is how many paths go through me. This is my DFS. How many paths go through me. This is my point of view. So he doesn't really care about the point of view of the others. He just cares about my point of view because he's like the king of the kings. So like, who cares about the others, right? So we do this DFS and we say that this centroid is now checked. We flag this because we cannot go through him again. This is our back door. We essentially, like every of these edge, we essentially put them a back door. We cannot go through them. They're fictional edges now. They're auxiliary. They're like back doors. They don't exist. Then we go for all of the V in the centroids, like, so for all of the subtrees here, so this is V is like here, like these are V's, the parents, the roots of each of my subtrees. But these are not necessarily centroids, not necessarily centroids. In these regions of the tree, I now need to find my fellow mayors, presidents, my fellow centroids. I need to find the centroid is like what is my best node that divides the best the tree. So like the most like powerful node in the tree, like whatever the balance of the tree, whatever. How do you imagine? And then I go through all of these subtrees essentially, and then I build them, and then I push the parent as my centroid. And now here you could have like here when like the parent of C of my centroid then is so you're actually, this PA is like the centroid tree, builds the centroid tree up. So essentially, okay, so what we need to do essentially for this problem. Yeah. A path is said to be palindromic if one permutation. Okay, so let's read this. We read A and B. I have them one indexed because the 0 index. I had some trick with the 0 index. I just don't remember back then. I had some trick with the 0 indexing. The parent of the first centroid is 0. I don't know. I had some trick with the 0 index, some problem. I don't know. So this is okay. So let's somehow build this string as cd s. Okay. Now we get this string. Now we need to go and actually do our centroid I mean, we already have the centroid decomposition done. We only want to now to make this data structure work. Okay, so DFS. So if you see something that I do wrong, you could just say, just tell me what I do wrong. Okay, where to start? It's very difficult in these problems where to start. Where to start is, okay, in the DFS, in the second DFS here, I need to do some special things. Why I do this? S to be equal to true, and here false. Okay, the distance, I don't care about the distance. So I could just delete this. Okay, so what is this S? S is my subtree here, like V. This V is my S. So the first node do the centroid. So this node that has the backdoor, the node that to the centroid that has the edge is my most important node. because this node will be the parent of all of the other centroids in here. That's why it's the most important node. So you have this node. This is wait just a minute. So no, this is not my node. This is my actual, like, this is my sorry. This is not my node. I'm doing this S is because if I'm the centroid, like this could be how can I am I like the king node, let's say, like the king node, whatever, it doesn't matter. Like, am I the centroid? If I'm the centroid, then I have to take a look at these subtrees as very special things, because other things inside this subtree doesn't really look that way. So this is like a special occasion. Am I the king? Okay. So each subtree will. So for each subtree, what I can do is I can do like a dictionary, right? So I can do like map. So what I can do is, like, if I'm a king, I could do like vector of map of vector of maps dictionaries as long as I'm a king. So it's either like if I'm a king is the GTU dot here let's say I can't use GTU dot size because GTU dot size accounts for no, it actually doesn't count for anything. Yeah, I can use GTU dot size because like the checked is only checked if and only if. I don't know if I can use this, so I will say like this. I will count how many children do I have. Then if I'm the king, I will go the children, otherwise I go 0. Can I create a 0 vector? Can I create with 0 space? I can, right? I think. Is it possible? If I'm the king, I will create these maps. If I'm not gonna create these maps. Okay, so my dictionary is like maps. For each subtree I will have like a map, a dictionary of this, of some things. Then, so if I'm not a king, so if I'm not the king, I need to have some map by reference here. And by default, I won't have map by reference, so what to do? By default, so here will be digs at like count. Some like count here, let's just like, this is like a pointer here, whatever, doesn't matter. That much. Let's do count plus plus, okay, whatever, blah blah blah. Text here I need a reference to this, but I don't have a reference. Can I do this? No, I don't think I can do this. Can I do this? Can I really do that? No, of course not. I would just create like a map here, just like a temporary map, whatever, just doesn't matter. Okay, so I will push this dictionary to my children, and then I will say, okay, children, do your thing. And each children, when it comes here, if I'm not the king, of course, I want the dictionary in my whatever my dictionary was. Whatever my dictionary was, I want to add in this dictionary my how do you say, my value. So there is like the, okay, I will say frequency like this. Now here another thing. So this is like, oh, this is insane how many things I need to pass through this DFS. So the frequency is another thing. Now the frequency at the first would be what? Would be 0 technically. But then each node I come to, I need to change the frequency here, XOR it by 1 over whatever this node is responsible for. And this node is responsible for S of u minus, so whatever the letter it is, here S of u minus 1, push 1. I flip this thing, this letter. Then I push the frequency. Do I push the frequency? I need to push the frequency down. And then I come to here and then I say okay, dict frequency plus plus. So I have all of these dictionaries now filled up. Technically, all of these dictionaries in my king node, in my Centroid, there would be like all of these dictionaries filled up. Now I need to merge them. Yeah. So technically I want to merge them smaller to large. Yeah, I want to merge them smaller to large, right? To just save space. So if I'm the king node, then I need to have some vector of order of merges, and this order will be my, like, how many children I have, and then I have this, right? Then I need to sort order on top of operator, and this order is actually what I'm sorting by. I think it's visible enough, right? I don't know if I need to zoom in more. I mean, now it's I think too big, but whatever. The order I'm going to sort by is like the dicts a dot size. Essentially, do I need to merge them? Wait. Do I need to merge them? Like the trick is now to, okay, so we have this, and the trick is now to go into one of these, and then I need to query to all of the others. So I do need to merge them. The order in which I'm merging them doesn't actually doesn't matter. Essentially, doesn't really matter. So I don't even need them. I will just comment this out. So it doesn't matter. The order to merge them doesn't matter. Only it matters that I have like the main dictionary in which I can so this main dictionary, like, how do I say, like master dictionary. This master dictionary contains all of the dictionaries of my children nodes. And this master dictionary is essentially, so I go through all of the dictionaries. What I can do is like this, dig in dictionaries, and for all of the elements in the dictionary, notice that this still lock in, so it doesn't really do this. It doesn't really matter. Master at element dot first plus equal element dot second. So we essentially merge all of them. And here, how can I? Okay, so okay, I merged all of the dictionaries. Now I need to do is to go through all of my children again and see actually how many children of these. Now this is only done once. This is only done in the king node. Pay attention to this. So this is only done in the king node. This is not done anywhere else. That's why it works so fast. And this is only done for. Also no. This master branch is actually not. Yeah, this master branch should be by reference here. Or I could do this. I could just do like map int master. This is why. I will tell you why. The master branch will be somewhere where like everything is merged except my my children. Okay, whatever. We'll get to this later. Also, these dictionaries here, these dictionaries should be actually also merged somewhere up in order to access them later, because I need to revert them. Okay, this dictionary should be up, but okay, we'll fix this. We'll fix this. So for each of these, I will merge to the master node. Then I need to do something else, and I'm really surprised how is this task 2400. This is division 1 plus division 2 round, and it's a lot of people solve it. I'm surprised. How is there like a better solution than what I'm doing, but whatever. Okay, so I haven't read the tutorial. There may be some trick. Do this quicker. Or maybe a lot of people solved after the contest, not on the contest. So okay, so this is the dictionary. All right. Now this dict, okay, this dict overrides it here, so I thought maybe it won't override. Okay, so we merge for the master, and now we need to answer some queries for my king node, for C. So to answer queries for C is just easy. We go over all of the nodes, all of my children, and we say if this is B or this is already checked, just continue, whatever. Okay, and then we need to, the answer here is the answer at my king node, so answer at U is something. So is this for every node in my dictionary, so for auto element index at v, no, not v, at count plus plus, and let's reset count. So for every this, it's like u is, okay, I'm getting the answer at u is, for every children, I need to look up, is this element, the answer is element.second times master at element.first, or I need to go through the through 20 iterations and I need to say answer to u plus equal that second, times master at element dot first x or 1 I. So this is said, okay, I flip this letter, and if there is something at the master that that matches to this, I say what is his count times what am my count, and this is what my u node is. And why is this fast? Is because like 20 times the log n times this is n, but this is n over amortized times n log n. So it's like n times log n times log n times 1, which is fast enough, I think. This could be faster. This could be faster. We could use this. We could use some special data structure, like tries, but it doesn't matter. Okay. So how to compute this? How the problem is? Here's the problem. We add to the master node, but we need to delete from the master node. This we need to delete after we have used it. So it's not that straightforward. It's definitely not that straightforward. We need this dictionary to exist even before the king has ever approached DFS, in order to delete it afterwards. Or can I delete it? Wait, can I delete it here? So I'm going, no, I can't. Ah, damn it. Damn it. Okay. Let's think about this. Let's think about this. How do we do this? How many hours? It's already 2 hours. I didn't even plan to stream 2 hours. Okay, so this is the best way to do this, is to create the dictionary over here before even step into the foot into the DFS. But now we don't know how many children we get. We need to count them. We need to count them, and we will do this. Just copy here. Now this is in the C here, so this is like the children of C if they're not checked. So I'm the king, so here it's the king. All right. So this is like count the king's children. This is count. This is dicts for every of his children. Fill them up. Now here, after we've built everything up, we need to delete. Also, we need, when we go into some node, we need to delete the dictionary that contains. We need to delete from the master the dictionary that contains this. Okay, so like okay. Here we need to pass. We need not only to pass dig, we need to pass also this. I mean, a lot of this function. Do I even need to pass this? I don't even need to pass this. I mean, I don't even need, but it won't make a difference. So it won't make a difference here. Oh yeah, this is vector of maps. And here I need to pass dicts. So yeah, in a lot of these references, but remember only one reference. Remember this: one reference is one long that you pass through the functions, through the stack. So usually you have like 8 megabyte. You have like unlimited stack on Codeforces. You have somewhere 8 megabyte stack on other one other website. So you could have Stack Overflow if you are not careful. But I don't think you will have Stack Overflow even if you pass like 20 longs in the DFS. Just so you know. But you have to be careful. I don't know how much it's like on IOI the limits, but you can ask or they're probably they say that they have Stack Overflow or they don't have Stack Overflow, whatever, it doesn't matter. But I remember one reference is just a long. Okay. Here. We need to, before we go build the other centroids, we first need to delete whatever we have added to the master. So that's here. Then we need to add it back. So also this add and remove this is not that big a deal. It's actually very. I mean, it should be still long and looking. Dict in the dictionaries. No, not dict in the dictionaries. Now here it's like this. Only the dictionary that we are. Okay, so okay, this is like this. Only in this dictionary. We need to remove this from the master library and then add it to the master library. Oh, also this, when you add it here to the master library, you have to account it for the centroid passing by, for my king centroid. Okay, this we didn't account for. Let me just think about this. What you need to do for the master library here. Master dictionary, whatever. Cool. It's like I'm kind of. Here it's not that simple. I mean, it's simple, but you have to account the centroid that you're passing by. You have to account his level, his value. That's what I don't account. Here I account the values of everyone. Actually, I count the value for the centroid, right? I count the value. Here this U is the centroid first. Then I go and I say, okay, this centroid, then I need to say that my element here in this times the master element. This is my centroid thing, my centroid value. I need to XOR it here. As far as because we're twice counting for, once in the master library and once in this in my account, my dictionary. So in my dictionary it's counted once, and then in the master library it's counted one more time. Yeah, my centroid value is this. Also, oh yeah, it's my centroid value is this. This should work. Okay, so we delete from the master library whatever my definition, my words were. Then I go through this subtree, and then whatever I do is basically this, and then I add it to the subtree again. Okay, so this kind of should potentially work, right? Okay, so another thing I need to print the answer here. Not sure if I got it. What else I missed? Answer. Okay, CD. Not sure what else I missed, but whoa, why answer? Whoa. Answer infinity. No. Wait, what? Oh, is a palindrome counted as one? Is one counted a palindrome as well? Yeah, this is not like, even like the king's frequency is accounted for. But why I'm not accounting for anything here? Oh. Okay, that's weird. Okay, let's print out the master dictionary multiple times. So for each centroid, let's print out the master dictionary. Like what? Doesn't even come here, or is the master empty? Okay, is master empty? That should not happen. Dictionary, if it's a king. Dictionary is my reference dictionary. Dictionaries is here, then okay. Oh no. This is only if I'm the king I can reference this. Oh yeah. My dict is only is like it. Am I a king? It's like this, or I'm this. Okay, some random numbers, whatever. Oh, something's broken here. Wait, if I'm the king, then I have to account your dictionary. Otherwise, it's like just pass it through. Okay, why is my frequency 0? Why is my frequency 0? integer minus s is this. This is, oh, I'm querying. I'm reading queries. What the? Totally bad. Okay. Wait, this is not correct. Whatever. It's definitely not correct. Okay, what is the frequency here? So what is the... This is still not correct. Oh, STU, yeah, of course. It's the U's are 1 indexed and this is 0 indexed. Of course, and I never read it before I build it. Wow. Okay, now makes sense. Now something makes sense, but okay, still okay. So the frequency is I think it's fine. I think the frequencies work okay. Now, things that don't work is whatever in the dictionary is, because there are a lot of zeros in the dictionary for some reason. Yeah, of course there will be zeros. But in the dictionary there is no way this large numbers can be created. So the frequency doesn't work. Or I have some reference bugs, so whatever. If you catch my mistake, just please tell me. There's no way this huge numbers. So UNV and master node. Dictionaries count. I'll see how these big numbers can be ever created. This is shift SU minus A. Is there anywhere this could be big enough? Anyhow is this big enough? No, this is not big enough. Okay, so what's wrong? Am I pasting everything? How is this frequency wrong? I'm baffled. How is in the dictionary something which shouldn't supposed to be? EL dot first. the dictionary that count. This is the children's dictionary. Oh, this is here. Okay. So this is like I'm asking for it here. Okay, that's kind of fine. That's kind of fine. Okay, whatever. Yeah, okay, that's kind of fine. I'm asking for it. That's why it exists in the dictionary. Okay, so we need to fix how these dictionaries are being handled here. Instead of this, maybe this dictionary would be better if I'm actually doing this it master.find this, then if it is not master.end, then it is like this, and this should be the same as well here. Without this, so I don't fill up my dictionaries with fake things. Okay. Okay, so from node C to node U, you have some frequency here, which let me just see if that's correct first. So from node, okay, so let's draw this tree here, or we already have this tree. We don't have this tree. Let's draw this. So from 1 to 3, 4, and 5. Okay, whatever. We have set, so from 1 to 3, this is A, B, C, and then yeah, we have 7, because it's like A is 1, then B is, and then that's 7 in binary. From 2 to 3, we would have B and C, 6. Yes, we have 6, and so forth. Okay, so 3 is our centroid. 3 is our first centroid. This is the king of the kings of the kings. So this is like our first centroid. You see that it's like in the middle of the tree. That's not a great crown at all, what I'm drawing here. Okay, so this is my centroid. Blah, 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 blah. Okay, so I'm a king, and I say that for all the dictionaries, I need to merge them to the master node, of course. I need to merge them to the master, and then I go through here, I find, oh, actually, I merge them at the end here, right? That's why I'm overcounting. Or do I? No, actually, yeah, I can merge them here, but then I need to unmerge everything which is being in my dictionary. So I need to do the same thing here, what this thing is doing. you have to participate to see the results. And yeah, so like, can we somehow get the results from someone that participated? I really want to see, like, in Slovenia and Macedonia, when which guys and how much they did. Can we possibly get the results? Yeah. Like, send to the Discord channel some screenshots. Okay, so I unmerged this node, but I merged them in the now I may do this like more efficiently. So like unmerge and then merge. And then here, okay, so here this is unmerge and then merge, because we don't want to have any dictionaries here, but for every of this we need to do this and then this and then so forth. So unmerged from the master and then merge again. Oh, no one participated from Slovenia. No way. That's a bummer. I didn't expect that. Usually we have some guys here participating, but didn't expect that. Especially like, okay, now all of the competitions are a little bit on pause, but it's like for the next semester, so from September on, we have again competitions. We have CERS, we have some other competitions. So I would seem to the Creation Olympiad is a very common thing over here to participate in, right? Okay, so we have unmerge, merge. So this 6 bothers me. Here I should undercount something. So these zeros are fine to me. The 6 is not fine. I should undercount things. Here the 6 is like a special, like, okay, I get why it's like this, because in this centroid here I have the most nodes, so if I root the tree in this centroid, I get like this something. Yeah. Let me just draw this how they're ABC BB. So ABC BB. So I get B, B, and B. So I'm overcounting by half, right? Is that correct? So from here I'm overcounting by half. Yeah, that's correct. So instead of not overcount by half, what we'll do is we will merge. We won't merge anything into the master node at first. We will merge them later. And now this should be correct. This should be 3 now. Okay, now this is 3. Now this is correct. So the centroid here is correct, except when the 1, 2, 3. Right. Now the centroid node is not really counted. Yeah, the centroid node is okay. So okay. Okay, so this seems correct. Now I need to go to the other centroid nodes to see if that's so. What else should be counted for? The master node here, where we're deleting from the master something that happens in my subtree, is that correct? Is that correct? Okay, so we go to so what's the next centroid node? The next centroid node is the next centroid node should be 2. and this here. 2 and 4 and 5. So this is like very small tree here. So each node should have +1 by default, because palindrome beginning at this node and ending in this node is +1. But now I need to account. What I don't account is starting at this position. This I don't account. Starting at the centroid and coming to the back door. How do you do this? You do this by saying, okay, the centroid is here. You do the answer at my centroid should be okay, so what I will do is I will do this function here. What I'm doing, I will do it as a function. So count answer. This function will take some element, so some element, my centroidal value, my node, so u. This will take some element, which is a pair of int. So pair integer, some element, and then u and my centroid value. And now here I need to count answer, u, element, and my centroidal value. Here I also need to count the answer. And I need to count it at C. I need to count the element is centroid value is 0, but the element is a little bit interesting here. It's my frequency. So my frequency is the frequency on the path from me and the other centroid. So I could store all of the frequencies in some other map here, like frequency path frequencies. So these frequencies I will store them like oh, actually, yeah, like how do I store this vector of maps? For every node I store the frequency. Yeah. Okay. Path frequencies. The problems were good. Yeah, I would like to see the problems. The last year there were really good problems, so I hope this year they were good as well. What kind of techniques did it have? Or no, don't spoil it. Maybe some yeah, don't spoil it. The year before they had like persistency on the last problem, so like persistent segment trees. But I solved the last problem not using persistent segment trees, but persistent interval containers, like a data structure that I made it persistent, but not like truly persistent, but it passed like all of the cases, so I was surprised. Oh, yeah, thank you. Yeah, I will look at them later. Let me just quickly solve this path frequency. So path frequencies. Path frequencies will, okay, so here when we add to this dictionary, we'll also want to add something else. We want to add path frequencies at my centroid node to myself is this frequency. So this is like on the path from my centroid node to myself is this frequency. This will be n-log n paths. Just have this in mind. these paths will be, and okay, these are all the only paths we care about, and here we will use them. We will say count the answer. Okay, so I'm at this centroid, and I know what is my like parent centroid, so I can do like frequency. So I need yeah, I think I can count here. The first problem is really nice, partially because I only managed to solve that one. The last year I didn't even manage to solve the first one. So like I don't know what like happened. Like I could solve some subtask of it, but I couldn't solve the whole problem. And I didn't solve the first one. I didn't solve the second one. I didn't solve the third one. I solved the fourth one. I had like some subtasks on some problems, and I don't quite recall. But it was crazy, like crazy how difficult the problems, like how easy the problems seemed, but it was actually like, I don't know, I didn't have any ideas. They were all ad hoc or something like this. There were no algorithms, and then the fourth problem I solved it with some like data structure that I come up with like on the fly, and I didn't even participate in like ordinary. I was like on somewhere, but I came home, and then I wrote the fourth problem. But it was crazy how it passed. Like I was surprised. The third and the fourth only have one correct. Yeah, I mean now like I was surprised because like maybe the test cases were weak, but now this year they probably the second problem no one solved it. This is crazy. Like how hard is this to live? Like if no one solved the second problem, you know? Like I don't know. But okay, the path frequency from my centroid, from my parent to myself. So this is like my path frequency, and this is like 1. Okay, so do we account for something else? Okay, we now account for everything except something. So okay, so so what we don't account for. Okay, so how what is that we don't account for? So from the path to this, I go into this dictionary and I say what is this, and then okay, so what I'm actually imagining here is like, okay, I'm some centroid. So this is like another representation of this, what I'm saying. So this is my parent centroid. I'm a centroid in his subtree somewhere, right? This is me. This is me. There is some path from my parent centroid to me. And this is the path frequency of my parent centroid to me. Now we need to account in the master. What happens in the master branch? In the master, not branch. What I'm saying. In the master dictionary. In the master dictionary is everything except what my subtree contains. So everything that passes through the parent centroid is in the master dictionary. So there is some path here in the master dictionary that comes to my parent centroid. Okay, then this path is like, okay, so what is my parent centroid to here? Do I need actually to I'm not sure if I overcount the parent centroid the parent centroid's value one more time. If I need to do like this. I'm not really sure if I overcount the value of the parent centroid. I'm not sure. So we will So it doesn't seem like. It doesn't seem like I'm overcounting the value. But okay, so this is the case. So this comes to me. But then there is a case where from this value is now the master branch. If there is some node here, let's say there is so there is some node which is in some subtree of my centroid. This node here, let's say E, this node, the master for this node now extends and this, like the blue thing here, extends to get everything except the subtree of where this E node is, because this E node will somewhere connect either to here or to here, my subtree, or to here and to other subtree. Okay, so how is everything here? Okay, so this is what worries me about this. Do I count this value or do I don't count this value here? So let's do this. My centroid value is counted twice. That's correct. My centroid value here. So why is this 1? So 1. So if I go back to the tree, in this tree there is only one path passing through 1, and it's a palindrome. And that one path is A. So when I come to 1 as this myself, I need to count the answers. I need also to count myself as this one node, right? Okay, so here, if I count +1 on the answer as myself, one of the nodes, I am overcounting the last 2. So I'm overcounting something in the last 2. So in 5 and 4. So in 5 and 4, these are B's here, and these are both centroids. And this centroid says, okay, to my parent centroid, I have like the path frequency. The path frequency to my parent centroid, it accounts for B and accounts for C. But then accounts for some, then I need, essentially I need to under account the path. Yeah, I need to do this. So I think I need to account for the parent centroid. I think I need to do this. I'm not sure. It doesn't change. Because like I account for, okay, what is P? Now P, C, and path frequency from P to C. If that's, oh, path frequency from P to C. Okay. P is 3 and 5. The path frequency is 6. Is the path frequency 6? The path frequency is 6. That's correct. Because B and C make 6 in binary. Okay, so all right. So is there like a difference if I unaccount this like that? No, there's no difference. So C is accounted for. Now we need to know how many paths go through B here. How many paths go through C here with paths frequency. Okay, so let me just take a look at the master. What we're looking in the master is the following. Frequencies, we're looking at this, and we're looking at the master is the following. We'll look for frequencies that are equal to B and C. So we're looking at frequencies that are equal to what is this, 6, right? So it's 6 and there are 2 of them. This is not correct. Oh yeah, this is correct. There is one like that and there is one like that. So this is correct. Okay, this is correct. Why am I overcounting something then if this is correct? So there's 2 times 1, that's 2. And then there should be counting answer. Oh, and there is like a language. Oh yeah. I see what's wrong. Well, I see what's bothering. It's bothering that, okay, this 6 here is also XOR with this is so no, this shouldn't be correct. Can we XOR all of these? Yeah, we can. Right. So we have A, B, and C, and then we have A, B, and C, which make one path. Then we have A, B, and C from 2 paths, and then we have C. Oh, wait, what? Yeah, we have C, and then B, but this C is not, is it accounted for? No, this C is not accounted for. This is accounted for as far as I know. This should be accounted for. Wait, let's see what is accounted for. Let's see this. So let's see this. It's accounted for el dot first it dot first accounted for. Something is not right. Okay, accounted for is here 2 and 3. So 2 and 3 is accounted for. How is 3 accounted for? 2 and 6 is accounted for, yeah, but how is 3 accounted for? Three, wait, el dot first is el dot first is the frequency XOR this XOR my centroid value, the frequency XOR my parent node, so XOR C. So the frequency at this node is BC. XOR C is it's only B. It says like that. Then 3 is accounted for. Oh no. Three cannot be accounted for. 3 cannot be accounted for in any way. This is a mistake here. We go through all of these, but if and only if this here is the same. If and only if this no, technically, wait. Do you guys see the problem somewhere? We're so close into solving this. I really want to solve this. See, okay. Should I count the parent though? Should I count the parent centroid? That's my problem. It's always my problem, like double accounting stuff. Okay, so my parent, if my parent centroid is accounted for, the problem is that if I have two paths, and this is like some parent, it doesn't really matter, parent. There is one path that accounts the parent from this side on. And then there is one path that accounts the parent from this side on. So this parent is twice accounted for, and thus if something is twice accounted for, it's not accounted for because of the parity. So what you need to do is account it 3 times. This parent node. Okay. Because I'm this node and there is some like path that is in the dictionary. This is like this path here is in the dictionary. So master of like the value of this path is in the dictionary. So it says like it's one path like this. And then I simply ask, okay, at the parent node, okay, at the master node, how many paths do, so I have some value of this path which I know. This is the path frequency from my parent to my U centroid or whatever. This I know. Then I need to XOR this by the parent because I don't need to include the parent because here it's already included. And then I take a look at this in the master. Or I can change one more thing here, because essentially if the master, how do I do this? Essentially there need to be like like if I have something in the master node, and then if I have something here which differs by 1 bit, I could change this 1 bit and find it in the master. Yeah, well, yeah, I changed this 1 bit and I find this structure in the master node. That seems okay. It seems okay. It's just the way here it works, because we undermine the this centroid we deleted, essentially what I'm getting here is I'm getting el.first and el.first I'm getting 2, which means that I'm getting only b. So I'm getting only this node here, this b node here. I'm only this node getting. And I'm asking in this structure, is there someone, but is this structure actually, does this structure actually contain my centroid? Or it doesn't? Yeah, this structure contains my centroid. Always. So I'm asking in this structure, so this structure is, here says there is one path with 3. So what does that mean? 3 is in binary 0, 1, 1, which means it contains only A and B. So which path contains only A and B? This path contains only A and B. But this path should contain the centroid as well. I don't see how the centroid is not contained in this path. The master should never be allowed to not have the parent centroid here. Something is wrong. Something is wildly wrong here. Just okay, so from the dictionary I delete from everything from the master's dictionary. I added from the dictionary here I add to the master dictionary el.second, el.first from the dictionaries.count. Of course. This. Now we're over counting a lot. But this answer shouldn't be 1 probably. Let me just... okay, so we're now over counting something else. So we fixed one thing and then we broke one other. Okay. So in the dictionaries I will compute through the centroid. Then it could happen that in the master dictionary I will compute to the centroid node. But then as I go down the tree, as I go down the centroid nodes, then I have to be really careful here. Now it changes something. Now here it changes some other thing. Here it changes if I want to compute the this changes here. What I want, the parent answer, this is my this answer. For every children, if I compute the parent's answer, if I compute it here, now not only this changes, but it changes, like this is the frequency. This is some frequency that is being set from above. And this frequency is set here from path frequency at C at V. No, this frequency is set from path parent to path C. If P, yeah, whatever. I think this will work. This is like propagation downstairs. Now this frequency here, am I overcounting something here? So I have one frequency which goes for from the parent to this centroid. And then I have here another frequency that goes from the path from the centroid, from my parent to the centroid. There's this frequency. And now I'm overcounting one thing. I'm overcounting the parent here, right? The parent here is overcounted. The parent of the centroid is another centroid. Yeah, I think I need to undercount here S at P, undercount my parent. Also here, do I need to undercount my parent? Yes, I think I need to undercount my parent. Okay, this is even worse result now. So what am I missing here? So I have this centroid, have some parent upstairs. I have some path here. So I want to make the path from the parent to the center. From the parent to this centroid. It's actually not necessarily, right? Yeah, not necessarily. You know what happens? You know what happens with these like lock-end levels? You need to have lock-end masters here. And each master will contain different kind of frequency accountability. Yeah. No, this is implementationally hard problem. So you need to have lock-in masters, essentially. Right? Because what happens is you can imagine like this. You can imagine this you can imagine like you have one centroid up, you have one centroid up, you have one centroid up, and you have one centroid up. This centroid, we know that our master now here is like everything except so everything except this. But the problem is that to this centroid, every path that passes through this centroid accounts for this edge, but it doesn't account for these two edges. So every path should account for this edge. But we can't just like ordinarily change the master here, the master book. Or can we? Can we ordinarily change it? Because when I come to this centroid, I need to know how. I actually have to change this, the master thing. I need to account for this edge as well. Oh, you can do a reversing thing. There is one trick where like you could apply the transformation to the whole master by applying a transformation to the master down below. That could be a trick. In order not to have like lock-in masters, which is possible to have lock-in masters, there is a trick to apply. We're applying this transformation on the frequencies downstairs, and then now we need to change them here. When I add to this master, I need to actually add it with a transformation. Is that correct? Is that correct? So if I have U, I have some node here, some node Q, then this frequency is like this. It's like, okay, this path is everywhere except should I do this transformation? Maybe it's easier to make lock-in masters. But will it time out if I make lock-in masters? That's the problem. Like every master will have like some depth here, and this is 0. I would master at resize lock. I would have this, and then I would have, okay, so this is my depth. This is my depth in the centroid tree. This is at most log n. We know this. The next time I go down the centroid tree, I go depth +1. Here I go, instead of depth, just d is fine. Here I'm looking at what master. I need to look actually at all of these masters. That's my problem. I mean, it would be just times log n, but still. I think it will tally. This will definitely tally. Because I have log n times log n times log n times 20 times n. Right? I think so. I think so. How can we make this better? So we have this centroid. Everything in this master has to be accounted. Yeah, I don't need lock-in. I will try to make this. I'll try to make it without lock-in masters. Because this will tally. So this node has all of this here. This node will add something, but should add something and should add this here to the master. So everything that this node adds should be added specially. So this is how would we account for this. But because the paths are not the same, are they? No, they're not. If I have centroid here, then I have some child tree. How much? Oh I'm streaming 3 hours. I have some child trees. This path here to the centroid, to another centroid here, is not the same as this path to this centroid here. But we only care about this path, do we? Is there like another, like, easier approach to take care of this path, of this frequencies here? I wonder. Yeah. -1 output. Yeah, Blower Lake, you should go to bed. I will go to bed as well. I mean, I don't know. I may try to solve it at home and then stream what I have changed, because it seems that I don't know how to handle the how to efficiently handle. Now, this is not about the centroid decomposition. This is about just handling these dictionaries properly. If you don't know how to handle these dictionaries properly, then the centroid decomposition is probably useless. Like, that's the fact. Okay, we have centroid decomposition. It works. It will work if I know how to handle the dictionaries properly without a log-n factor again. Because you could add many log-n factors, and then you will see that it will tally. So, I mean, it's insane. It's insane. So here I need to take care of this path from the parent to my centroid, to where I am. I need to take care of this path when I go down, so I don't kind of wanna iterate through the whole dictionary to carry the path. I kind of wanna push it down. Maybe we could push it into DFS here. Is that the trick? Maybe here in the frequency we could push this path. So we're pushing here my frequency with this path attached to it, and then we're pushing at this path, okay, and then DFS to propagate. Yeah, I mean, yeah. I don't really want to see the tutorial, but here, what's the trick here? It's I would think that the master, my centroidal value on the dictionary is to I have like this, and then I mean, yeah, maybe I could iterate through the whole dictionary. Let's try this like quickly. So let's try this. So I have like some dictionary. So here I have some dictionary. I do this, and then what I need to do is just quickly to iterate over the whole dictionary with, for the master. So I need to iterate. Okay, so let's say like this. So I need to actually make another dictionary and then iterate it. Yeah, you need to propagate this value. I mean, it's hard to propagate the value. It's hard because you would take this centroid and then you would go So you have already computed some subtrees of this centroid, and these are already in master. These are already in master, and then what happens is this path here changes these subtrees. Okay, only these. And then you compute something else, and then these subtrees which are here are only changed by this path and not by this. So essentially you compute these things, but you need to change them when you're propagating them. So like instead of we're adding to the master here, we could delete everything here. We could delete from the master we could delete and re-add it again. That's one thing we could simply do without big deal here. I mean, it's again some factor, but shouldn't that matter? My centroidal value is this. So like, okay, update the dictionary. Oh no. This path is different. That's the problem, because like this path is one, but then there is this path, which is not that easy, because all of these should be changed, but not these here. So you could have two essentially masters. One master that would be on the parents node and one master that would be here. Okay, this is possible. This is possible. One master to the parents node and one master to here. Yeah, so I mean, should try call this one master. So this you don't add to the master, that's the problem. This you add to another map here. Let's say that this T map, whatever this T map was, I'm going to add to this T map this here. But now this T map is used downstairs, isn't it? Or no, this T map is not used downstairs. This T map is not used downstairs. So okay, dix elements, we add that. We count the answers in the master branch, but we need also to count the answers yeah, this is a little bit more complicated than what I intended to do. So you count the answers in not the master branch. We don't count the answers. Yeah, we count the answers in the master branch, but we count the answers in the master branch by different parameters. We do this. Okay, so I will stop streaming, not because like I could solve this probably like if maybe 30 or 1 hour maybe I would solve this problem. But I will stop streaming because it's getting a bit too late, and I'm kind of exhausted. So I will tomorrow maybe stream again, just because I want to practice a little bit more of these problems. I haven't solved a lot of square decomposition, but the technique is very straightforward. The implementations, however, are not straightforward. And I'm sure that if I go into the standings, I will see like probably better implementations, probably shorter implementations. But what I'm doing here is not very difficult to understand. It's only the problem is only just to implement it like you need. Just for example, this is just for example how powerful square root decomposition and how like what you can do with square root decomposition. I mean, not what you can do, but this problem band. This is a code from the Polish team. They have some LCA code here, and they will have some special functions where you could see if it's like on a path. And then this is the centroid tree. This is the square root decomposition. And look at the code. There's the layer. There's the DFS2, what we're doing. There's the decomposition. There's the update function. They update for like log n times in the tree. They also query. And these things are not easy to write, especially with this order of key. This like they have segment, like essentially they have these order sets for each of the centroid levels. In each level there are like sets that for each subtree you have like these sets. What we're doing here with maps, they are doing that with order sets. So this is crazy. This is crazy. And to code this in what, like an hour? Probably, right? They had to code this in an hour. Because there were like 12 or more tasks. I don't know how many tasks there were. So 12 tasks. They had to code this in an hour. In half an hour, if you want to solve all the 12 tasks, you have to code it quickly. But yeah, and they coded it, and it works, right? So it's very powerful technique, but it requires practice. And this is why the best way to learn something is to teach it, no? And this is why I want to make this stream, to just try out some centroid decomposition problem. And it turns out this problem is not that easy, even though it's like rated 2400. I mean, yeah, you just need to propagate through this master dictionary, but I'm not sure like will it TLE. So I want to write something that it will TLE. Because this is already on the bounds to TLE. This is already very close to the limit. So yeah, I don't like to but my brain won't work, and now I will spend like just an hour debugging this. Instead, I will debug it, and tomorrow I will come stream once again, just to show you where my mistakes are. And this is exactly what I said. The master dictionary should be changed according to these paths. And now these paths, I don't know if I need log n master dictionaries, or if I need, like, I'm not. Yeah, what you can do is like log n master dictionaries, yeah, because it's the same complex for each level. This dictionary that we'll have here, this that we're having this dictionary here, this dictionary here of all of my children, and I have like one dictionary that here I could have one dictionary that is master for this level, right? And this will be actually my merged dictionary. Something like this. And then I would have this master dictionary. I would then, when I'm merging these children, I would have like the master dictionary at this depth. This scared the shit out of me. Then I have my depth here. I have my depth, whatever, that doesn't really matter. When I'm merging this to the master dictionaries at this depth, I actually need to go through all of the master dictionaries here. Okay, so I need to go through all of the master dictionaries, and here I need to say, okay, this is my depth. Master dictionary, I don't care. Let me just comment this out. Now when I'm merging this, I will unmerge at my depth. I will unmerge them and then go here. For this you would have for like all of these master dictionaries, you need to remember what is the length of these master dictionaries to me. This is what I need to compute, to propagate through this DFS, right? And then so this is all I need to do. And actually this won't be more complex. I mean, it would add a little bit more factor, but these master dictionaries would be smaller than what I had prior, so it would somehow balance out, I think, at least. So here it would be like through all of them, for all of my master dictionaries that are through this depth, I want to count the answer, but I want to count the answer on the level. I want to count the answer. Here is like the path, some path. I need to add some path here, so I need to propagate this path. Wow, so many integers. I can't. Have you ever written a DFS with that many? With that many things? So this is the path, but this is not only like this path. You need to have log n paths. So you need to have like a vector of paths here, and this vector of paths should be passed by references, and then this here is like the dth path, the dth path to this dictionary, right? But d is only log n. So this is only log n. This is at most log n. This here, so this is most log n. So this, okay. But maybe I need a snippet where I will design the snippet such that like these pushes and pulls in the centroid decomposition, this is what we call like, we have pull. When you pull this information from the DFS2, you pull information from the dictionary here. This is like the pull, because you pull it up, and then you have these things that push down through the DFS, through the centroid decomposition. And these are much more harder to compute, much more harder not to compute. It's much more harder to wrap your head around how they work. It's not that easy. So let's say here I need another vector which has these paths, right? And then this build vector should, you need to add it here in order, like this will be an empty vector, but it will actually like be by reference, so I don't send, even though locand values is not a big deal to send them down, but okay, so this here, when I go to the DFS, I need to add the path vector. Also, I need to add it here. Now this path vector I will push on this path vector here. I will push on this path vector. I will push. I will push something. Path frequency from my parent to my centroid. I will push it here on the path to the path vector. So actually no, I need frequency this. So the frequency to here, to this guy, then and this still. So what I will do is like this. Frequency, I do this, path frequency at PC, then I push down the frequency, I push here down the frequency as well. But actually I need to do this, because you overcount once the parent. Now if the parent is equal to C, then I don't need to do this. If parent is not equal to C, then I need to do this. Actually, here, this I don't need to do this. If parent is equal to C, then it's like 0, then this. Parent is equal to C, then this. Then I push the frequency, and here I push the frequency, I push the path. What else should I push here? I push, wait, path is wrong here, should be path. Okay. Okay. So we push frequency path. Let's just delete this. So we change the frequency to this centroid from upstairs. Then we push it to the path. So this includes my centroid. This includes my centroid, so I will here it's count answer, so count, this includes my centroid. But actually no, I want to push 0 to my centroid, but all of the other paths to my depth is like path at I, path at I is like the path frequency PSC, something like that. And then you need to undo. Also, I can't push back here. I need to make this vector all zeros. So like something like 50 zeros. Okay, whatever. Okay, this vector is 50 zeros. Okay, so I push all the paths, get this frequency here, except my last path, because my last path is this path that does not have this thing here. Okay. So in the master, in D I'm gonna push this. Then I'm gonna go through all of the D's, and then I will do path D at this master. This master at D. Okay, that's correct. What else should be correct? What else should not be correct? Okay, here there is something like, okay, we need to go here. Then there is, so I need to go through all of these D's, which have little to no thing, and then I need to do master at D here. And here I need to, this is my, this is what, this is my, this is 0. I think. Okay, so we're getting there somewhere. Count answer. Yeah, this centroid value, this I don't know if this is ever needed. This is now not needed because this is, I'm counting the answer through this. Yeah, this is actually needed. Oh, this is actually needed. Is it needed here is my question. Okay, I will fix this. I will fix this. I know it's getting too late. It's 3.5 hours. I will fix this. I will debug all of these. What happens here? What happens here? Something is not accounted for, but the idea is this. The idea is this. I don't know if this will even pass, but if it doesn't pass, I think I know how to compute something else better. Here, instead of this log and factor, I don't know if it will pass. But let me just see on the standings what it is. Standings, let me just see. This guy took like 1 hour to solve this. So many people solve it. It's not that bad. But I don't know how they propagate this. Not really many people. If like 200 people solve it, it's not many people. Like, I mean, yeah, the guy took 2 hours to solve. Okay. So, yeah. Oh no, I will end the stream here so it doesn't, so you guys can go to sleep and I can go to sleep, but tomorrow I will revisit the problem. I will fix my bugs here. And this is the idea. This is the Centroid idea. And when I fix my bugs, we will submit the problem together and hope to get AC. So thank you guys so much for watching, and I see you in the next stream.